Okay, here are two more examples of simplifying roots, and I'm going to use the root property mentioned previously that we can separate this number into a product of numbers. And let me just show that since I don't have the property written up here. I want to know what the square root of 48 is. 6 times 6 is 36, 7 times 7 is 49. So it's pretty close to 7, but not quite if I were to approximate it. 6 point something, very close to 7. Okay. But if I want the simplified exact form, then what I want to do is represent this as a product such that part of that product, one of the factors or more of the factors, are perfect squares. So let me do that. What times what is 48 such that one of those factors is a perfect square? Okay, so we know that 6 times 8, neither of those are perfect squares. Let me reduce one by 2 and the other multiply by 2. So 6 times 8, instead of that, let's do 3 times 16. Yeah, that works. 3 times 16 is 48, and 16 is a perfect square. So let me instead represent this as the root of 16 times 3. I can separate it then into the root of 16 times the root of 3, and that was the property to which I was referring. Now I can take the square root of 16, which is 4, and I'm left with root 3 here. So 4 times the square root of 3 is the same as the square root of 48. And this is my simplified exact answer or form of the root of 48. Now remember, if that wasn't obvious, if you were trying to work it out mentally, trying to come up with those perfect squares, but you just couldn't see it, you can always start factoring 48 until you find what you're looking for. And you can take that all the way down to the prime factors if you want. Let's see, well, at least 2 goes into 48. I know that because that's an even number. So this is going to be 2 times 24. Aha, another even number. So this is 2 times 12, another even number. This is 2 times 6, another even number. This is 2 times 3, and now I've gotten down to the prime factorization of 48. So I could say 48 is equal to, I'm looking for perfect squares. For now, let me just write it like this. 2 times 2 times 2 times 2 times 3. Okay. This is 2 squared, and this is 2 squared. Or we could look at that as 4 times 4, which is 4 squared, which gets you to the 16 right away. But let me show the root of 48 as represented by the root of all these prime factors. 2 times 2 times 2 times 2 times 3. Now, anytime you have a pair of these, because you're talking about a square root, you can take the square root of that. The square root of 2 times 2 is just 2. In other words, the square root of 2 squared is 2. So this gives me 1, 2 from this times 1, 2 from this times, I'm left with the square root of 3, which produces 4 square root of 3. Same thing. Another way you could have shown this is the following. Let me just erase right here, and I will rewrite it the way that I did it on the previous video. I said that I was looking for perfect squares in those prime factors. Okay. So I could have said, oh yes, this is 2 times 2 times 2 times 2 times 2. Did I get too many 2s? I don't know. 4 2s and a 3. Which is the same thing as the square root of 2 squared times 2 squared times 3. Now I can separate this into the root of 2 squared times the root of 2 squared times the root of 3. I can square root both of these guys to get exactly 2 times 2 times the root of 3, which produces 4 square root of 3. So there are a lot of ways to look at this, but you can, if you'd like, just take it all the way down to the prime numbers if it is not immediately obvious what the factors of this number are that are perfect squares. And ideally, you want to try to find the largest number that is a perfect square, or that can be rooted to produce the thing that was squared. So 16 was the largest perfect square that I could find as a factor of 48. And so that was convenient, and it made the work getting to the solution fast. But again, that's not always possible at first glance. Let's take a look at the cube root of negative 72. And first ask ourselves, would we even come up with a real number? Because it's a cube root, we would, because a negative times a negative times a negative is negative. So that's okay, we can come up with a real number. And we can simplify this. Now, what times what is 72 such that we have a perfect cube? 72 is a lot of things. 36 times 2. But 36 is a perfect square, not a perfect cube. So I want to look at it a little bit different. And in fact, what comes to my mind is 8. So notice I could say that this is the cube root of negative 8 times 9. 8 is a perfect cube. So I can separate this now into the cube root of negative 8 times the cube root of 9. That index has to stay the same, okay? The cube root of negative 8 is negative 2. Negative 2 times negative 2 times negative 2 is negative 8. And I'm left with this guy, the cube root of 9. How do you know when you're done? Why am I not messing with the 9? Well, there are no perfect cube factors in 9. 9 is 3 times 3, and that's it. So I know that there's nothing more I can simplify here. So I'm going to take this and leave it at that. Now, how could I have done that with the prime factorization method? Again, I can look at 72 and start doing the factorization. It's an even number, so 2 times 36, there's an even number, so 2 times 18, there's another even number. Okay, 2 times 9. I could take this all the way down to 3 times 3. Therefore, the square root, or excuse me, the cube root of negative 72, cube root of negative 72 can be represented as the cube root of negative, all of these guys multiplied. The negative, you can look at that as negative 1 as well, okay, times 72. So I'm going to put here 2 times 2 times 2 times 3 times 3. Now notice again, I have a triplet here, and that's right here. And now I'm looking for a triple because I'm looking for a cube. 2 times 2 times 2 is a perfect cube, 2 cubed. So I am going to cube root this 2 cubed to just get 2. Now you do have to be careful with the negative. And I know I'm allowed to get a negative because negative times negative times negative is positive. I could say that this is the cube root of, let me call that negative 1 cubed to be kind of tricky. That produces negative 1, so that's okay. This here is 2 cubed. This guy is 3 squared. So when I separate this out, I can say, oh, I've got the cube root of negative 1 cubed times the cube root of 2 cubed times the cube root of 3 squared. And notice how the power here of 2 is less than 3. That's another indicator like, okay, I can stop right there as far as the last guy is concerned. From here, the cube root of negative 1 cubed is negative 1. So this gives me negative 1 times the cube root of 2 cubed is 2 times the cube root of 3 squared. I'm just going to leave as the cube root of, in fact, now I'm going to call that 9 because there's nothing I can do here to cube root it. Negative 1 times 2 is negative 2, so we end up with the same thing we did here. Negative 2 cube root of 9. And certainly it does take a little bit longer to get to this place if you take it all the way down to the prime factorization. But sometimes you have to. Sometimes it's just not obvious. So there are two more examples of simplifying roots. Let me move on to rationalizing in the next video.